So, good morning. It is my pleasure to introduce you the keynote speaker of the session on water and biogeochemical cycles in Earth system models, who is Bertrand Guenet. As he already gave a very beautiful glance of his research topic in the opening course, I will be rather short. So Bertrand works at the Laboratoire of Géologie of the École Nationale Supérieure. He spends his career on studying the carbon and nitrogen cycle in soils, both via observations and modeling. And now he works on improving the soil carbon scheme in land surface models. And today he will give us an answer on the question, are Earth system models adapted to study soil carbon dynamics? So please welcome Bertrand Guenet.
Thank you very much. So thanks for the invitation. It's a great pleasure to be here with you, and I will try to bring you to a journey where we'll try to answer the following questions. So are Earth system models adapted to study soil carbon dynamics? And actually I should have been more precise in my title, because I will only talk about soil organic carbon in that case. But well, still I hope you will like it. So you know this this very clear overview of the global carbon cycle, and basically I decided to show you this plot to show that in the soil you have a large stock of organic carbon. If you look only at the mineral soils, you have 1,700 gigatons of carbon at global scales. And if you sum up the permafrost, you have to add 1,400 more petagram of carbon. And at the end, the soil participates to a huge flux of exchange of greenhouse gases and CO2 in particular with the atmosphere, because the heterotrophic respiration, which is basically the respiration of the microorganisms that use the soil organic carbon as substrate, they participate to this respiration flux here, and it's like around 50 petagram of carbon per year. So and just to keep in mind the order of magnitude, the anthropogenic emission are around 10 petagram of carbon per year. So it's a huge stock, and it's a huge flux. Maybe it's to have a like a oversimplified representation of how it's going on. You have CO2 in the atmosphere, you have photosynthesis here, the plants, they create biomass, and then at the end of their living period, they have fresh organic matter, so like litter, for instance, that goes into the soil. And then this fresh organic matter is turned into soil organic matter by the microorganisms, and this microbial activity leads to release nitrogen in the system, or nutrients in general that are used by the plant, but they also leads to increase the CO2. And this microbial activity on soil organic matter mineralization is mostly controlled by temperature and humidity of soil, but also by the amount and the quality of the inputs. But something that is important to keep in mind is that with anthropogenic emission and an increase of CO2 in the atmosphere, this cycle tends to accelerate. So we have more photosynthesis and we have more carbon input, and it seems that we have more microbial activity and more CO2 emissions. And this may impact the air temperature and the soil moisture. So here, with this very simplistic scheme, we clearly see that the soil are really at the center of feedback loops between the carbon cycle and the atmosphere, and that's why it's important to study them in details. One of the tools that have been quite used to study the soil carbon here are the models. So I don't know if you can really see here if you're in the back of the room, but basically here you have the number of publication using model from the 30s up to the years 2000s, and you can clearly see an increase. Obviously, when we start to add computers, we use model more and more, and here on the bottom you have the total citation of different models. And what you can see here is that actually most of the community, they use basically the same model, that Century, ROTC, DNDC, and so on, and they are all based on the same philosophy, which is the first order kinetics, but I will explain this a bit more in details later. Also, something that is important to keep in mind is that models are just tools, so they need to be used for what they have been developed at, and you can use model to look at very, very small scales. You can look at ecosystem scales, and you can also look at the global scales. And so the topic of today will be mostly at the global scales, because we will talk about these Earth system models. Let me define what is an Earth system model. So an Earth system model is basically a 3D representation of the atmosphere, the ocean, the sea ice, and the land surface. So you have different modules in these Earth system models. You have an ocean model, you have a land surface model, and so on and so on. And so they are all developed by different groups, and those groups, they work together to, at the end, produce an Earth system models. And so in those Earth system models, you have a quite important coupling between the climate and the biogeochemical cycles, in particular the carbon cycles. And if you look at the soil in that case, so the soils are important drivers for the water cycle, for the carbon cycle, for the nitrogen cycle. So the soils are really a key component of these Earth system models, and that needs to be really looked in details and be evaluated in details also. So I will show you this plot. It's come from a publication by Keynote Brown. It has been done with not the last simulation of the CEMIP exercise, so not the last modeling intercomparison exercise where most of the Earth system model participate. It's with the old one, but the results are still the same, and I will show you later a bit what are the results. But I think the way the Keynote Brown present the results are maybe more comprehensive than what have been done after. So basically what you have here is that you have the total soil carbon, and the different bar plots are different models, or the first one here in red is the observation. And then you have this area here which corresponds to the uncertainty around the observations. So you have two ways to look at this plot actually. You can somehow remove your glasses here, and and then you say, oh, okay, it's not too bad actually. Most of the model, they are within the range of uncertainty. And so you can say, okay, like the Earth system model, they are good tools. You can reproduce well the total soil carbon stocks. But if you start to really put your glasses, let's take the example of the IPSL model. I'm fine to criticize the IPSL model because this is the one I'm working with. So you can see that here, you are very close to observations. But if you look at the details, and you look at the NPP, so the input of carbon into the soils, and the turnover time of the soil carbon, actually, so it's the same kind of plots, and you have the observation here on the left part, and then you have the different models. You can see that the IPSL has a too low turnover time and a too high NPP. So actually, you had this good result, but for bad reasons. So you have a bias compensation in this kind of model, and if you look at all the models, actually most of them have a bias compensations. Here, it's just an example, so the numbers don't really care, but it's just to say that it doesn't have changed much with the new CEMIP 6 exercise. We are working on the CEMIP 7 actually, and hopefully things will be improved a bit. But okay, why can we have good soil stocks but for bad reason? I told you about bias compensation. If you look at the soil in a very simple way, it's a dynamic pools where the stocks is the result of the difference between the inputs that are litter production, for instance, root exudate, or like manure amendment and so on, and the output, which in the model is mostly microbial respiration. We don't have erosion that much represented in this kind of models. So if your two fluxes, the input fluxes is correctly constrained, the output fluxes is correctly constrained, you will have the good soil carbon stocks. But, if the input is too high or the respiration is too low, then you will have another estimations. And the same, if the inputs are too low and the output or the outputs are too high, you have an underestimations. But if both are too high or both are too low, you can have bias compensation here, and you can have like the good stock but for the bad reason. And the idea is to have the good stock but for the good reason. So let's enter a bit the detail of how those models are designed. This is a representation of the century model, but let's say that it's quite representative of all the different models. It's basically based on pools that are conceptual, so you can't really define them. When I talk to my colleagues who do soil carbon measurement, and I told them, please, could you estimate how much of this pool is in your soil? They told me it's a nonsense question. I can't do it. Your pool is purely conceptual. So it makes, obviously, the evaluation of this kind of model a bit more complicated. But basically, you have the input of liter here. This liter is then decomposed, and it feeds different pools of organic carbon. So in the case of Century, you have the active, the slow, and the passive pool. The main difference between these three pools is their turnover time. And the key equation that you have in this kind of model is this one. So basically, the dynamic of soil organic carbon in a pool is the difference between the input coming from, let's say, the liter, minus the decomposition, which is controlled by this first order kinetics. And you have K, which is the decomposition parameters, multiplied by the amount of carbon that you have in your pool. And then you have two rate modifiers here. This theta is supposed to represent the effect of soil moisture on decomposition, and this tau is supposed to represent the effect of temperature on soil decomposition. When you look at these kind of schemes, and if you're a bit experienced in soil science, you immediately identify some key mechanisms that are not represented explicitly in the model. For instance, if you're more some kind of a microbial ecologist, you will see, oh, I don't get why there is no microbes here, whereas the microbes, they are the main actors of the decomposition, why they are not explicitly represented. Okay, if you're a chemist or if you're a physicist, you will have also immediately something that jump up to your mind and say, there is a key mechanism that I know which is not represented. Okay, but this being said, it's difficult to implement those kind of mechanisms. The people that develop Earth system models, they are not totally ignorant of the literature. It's just that sometimes you also have some upscaling challenges and so on that we can, if you want, discuss later. But also something that you have to keep in mind is that, is it really important within an Earth system model to have the good stocks? Maybe it's not so important. This Earth system model, they are about fluxes. What you need to have in your model is the good fluxes, is you have to have the good exchange between the atmosphere and the land, or the atmosphere and the ocean, and so on and so on. Okay, because the climate system is actually more responding to the flux than to the pools. Maybe a bit of clarification in terms of vocabulary here. You have the soil respiration, but the soil respiration is not the heterotrophic respiration. The soil respiration is the respiration from the roots plus the respiration from the microbes, okay? And this autotrophic respiration is the growth primary production minus the net primary productions. And something which is interesting to know is that this Earth system model, they have been never evaluated against heterotrophic respiration fluxes before, mostly because there was no product that were available at the global scale. So you can partially evaluate this flux if you look at the net ecosystem exchange, because the heterotrophic respiration participated to the net ecosystem exchange, but it's still like a partial evolution. As far as I know, the first global product was published by Soshi Hashimoto in like 10 years ago, and then since then there was a couple of estimations that were available. But also something important to keep in mind is that most of them, they use the same data that are coming from the Bond-Lamberti databases. But still, at least now we have such a product. So in a paper we published last year, we tried to estimate how those Earth system models are able to reproduce these heterotrophic fluxes. And so we use 13 Earth system models that all participated to the SEMIP6 exercise. So this, just to remind you that this modeling comparison, they are a key input of the IPCC report. So they are really like all the groups all over the world that try to follow as much as they can the same modeling protocol to be able to then do a couple of intercomparison with the different models. And here, in our case, we work only on the historical simulations, and we compare the outputs of the model to 3 observation products. The first thing that we can see here is that we have the total heterotrophic respiration over the lens. In blue, you have the different models, and in orange, you have the different observation-based products. You have basically the orange dot line is the median of the product, the blue dot line is the median of the models, and the orange area is the median plus the uncertainty coming from the observation product. So here, what you can see is that indeed, for the fluxes, you have a lot of models that are actually within the range of uncertainty, including the IPSL one, and you can say that, okay, the total flux actually is not that bad compared to what we know. And it's somehow surprising because, as I was telling you, those flux could not be evaluated before because we did not just have the product to do it. But if you look at the spatial bias, here you have a bit of spatial bias. So what I'm showing here is a map of residuals. So it is basically the model median divided, minus the median of the respiration product. And here you have a latitudinal gradient, here you have a longitudinal gradient, but maybe like the take-home message of this plot is that we may generally have the good flux, the good total flux, but we have some spatial patterns. We have overestimation in some places, we have underestimation in other places. So the spatial diversity of the situation is not well represented by the model. And when we try to understand what are the key drivers of these residuals, something that we observed is that if you look at the evolution of the model residual here, so depending on different driver, so you have on the bottom right mean annual temperature, on the bottom left mean annual precipitation, on the top left soil organic carbon, and on the top right the residual on the net primary production. And something that we can observe is that actually there is a trend, somehow linear, almost linear, between the mean annual precipitations and the errors done by the model to reproduce the heterotrophic fluxes. So it suggests that the way we represent the effect of soil moisture on the decomposition is probably oversimplified, or at least it's not the really a good representation of what's going on in reality. So basically, this is what the reality looks like, okay? And this is what is done by the Earth system model. So we get somehow the main pattern, but we can see that there is room for improvement in the details. Okay? So this came up with this paper, which is actually in preprint. It's submitted to ESDD, where we try to use an observation-based moisture function instead of the classic one that was used in the Orchidea model, so which is the land surface scheme of the IPSL model. You have this dotted line, which is the relative soil respiration. So it's basically this theta function. It goes from a threshold of 0.25 up to 1, and it depends on the water saturation here. What you can see, so here is the default function that we have in the model. What you can see here is that the model assumes that the more saturated you are, the more close to saturation you are, the fastest is the decomposition. This totally overlooks the fact that if you're close to saturation, at some point you're also oxygen limited, and so you should reduce also the decomposition. And this is something that you can see if you look at the same kind of function that were fit on observations. So basically, what we did is that we compare a model version when we have this function versus a model version where we implement these different bell-shaped curves, knowing that the different bell-shaped curves parameters depend on soil texture, depends on bulk density, and so on and so on. And what we have here is, so we compare here so this is the total carbon stocks here. We have what was done with the land surface model Orchidea without this new function, what we have with this new function, and here we have two different products. So what we can see here is that with this new function, we have a much higher soil carbon stocks in the models, which is much close to observations. It's important to note here that in this version of the model, we do not have organic soil, so we do not have explicit representation of peatland nether permafrost, which explain why we still are a bit far from the observation product. And in particular, you can see that the main differences are in the boreal regions. And then when you look at the respirations, actually the effect on respiration is not so big. So the initial signal on heterotrophic respiration was not bad, and it's still not bad. So the take-home message of my presentation would be, okay, if you remember, the initial question was, are Earth system models adapted to study the role of soil in a global change context? I would say that they are not too bad to represent the actual stocks, but most of them, they have bias compensation. It may be bias between mechanism, or you can have like also spatial bias compensations. You have one key point is that these Earth system models, they obviously oversimplify the reality, and when you oversimplify the reality, you make a lot of underlying assumptions. In one of these underlying assumptions is that the balance between the mechanisms are the same under climate change. This is probably not true, in particular when we talk about microbial dynamics. Nevertheless, we have a lot of encouraging results from the new generation models. I show you just one example, but there is a lot of groups that are working on this in the world, and I'm happy to take any questions and to discuss this later if you want. And yeah, I just wanted to thank all the people who participate to this work. I do not put any name because I will likely forget someone. Yeah, thank you all for your attention, and I'm happy to answer any question.